I'm proceeding now with the next speakers, and we will have all the question at the end of our session. So the next speaker is Marta Blangiardo. She is a professor of biostatistics at Imperial College London in UK, and she's going to talk about a dependent Bayesian Dirichlet process model for source apportionment of particle number size distribution. To you, Marta.
Thank you, Monica. Thank you, everybody, for being here. It's really nice to be able to bring our experience as well, and it's going to be a slightly different talk from the one Matt just gave, because this is a bit more specific on actually what we did in the project, which was kind of like a very applied, it stemmed really from a very applied problem related to the apportionment of particulate matter. So I am gonna just start, if this works, yes, with a question which is it's a bit of background. So it's kind of like, is air pollution really that bad? And obviously the short answer is yes, of course it is. But I find interesting just to show these pictures, because I don't know if you have seen this before, but a few years ago, can't really remember which newspaper, but they sort of like showed these pictures of cities across the world and what they would look like if air pollution were visible. And you can see here London, for instance, with the Big Bang at the back, and you see this kind of like foggy thing going around. And it gets worse if you look at Istanbul or even New Delhi. So really, it gives you this idea that, well, you know, air pollution is really pretty bad. If only we could see it, you know, we would appreciate more that actually is a big problem. And it is a big problem, which, you know, air pollution is really quite connected and intertwined with climate change. In the sense that, for instance, the gases, they are kind of like increase the air temperature, like carbon dioxide and methane. And one thing which, you know, I found out quite recently was that the PM in very remote places like the Arctic apparently cast shadows on the ice, and that contributes to the ice melting, which is really terrible. And then obviously, if it's hot, the smog gets worse because there is more ultraviolet radiation. So there's no surprise that the air pollution features in the Sustainable Development Goals, particularly in this 3.1 listed here. So it's trying to reduce the deaths and illnesses from air pollution, access to clean energy, and also reduction of environmental impact of big cities, which is really relevant, particularly now that we just really passed the 8 billion people on this earth. And what I find really scary is that according to WHO, basically 9 out of 10 people live in places where the air pollution is really bad. So the PM 2.5 concentration exceeds the annual limit set by the WHO, which is 10 microgram per square meter. Obviously, so air pollution is bad for the environment, is bad for the health as well. And we have plenty of studies showing that actually there are deaths related to air pollution. And this very new study from actually a colleague at Imperial, they found that about 6.5 million deaths each year in the world are due to air pollution. There is also synergistic effect between heat and air pollution for all causes, but also for specific mortality and hospital admission like cardiovascular and respiratory causes. And this obviously gets even more important considering that, you know, that the climate is changing. So basically not all the studies, but most of the studies so far in the epidemiological clinical literature, they tend to focus on one pollutant, 2 pollutants, and obviously, if you think about it, what we breathe is really a mixture of things. You know, we don't really breathe one pollutant at a time. So really, there has been this kind of like shift recently towards this multi-pollutant approach, and even more if you think about PM, so particulate matter, which is really just giving you an idea of everything, all the particles below a certain size. really this could come from different sources. So to give you an idea, I hope you can see the picture, kind of. So if you imagine that this is a city, not really a good place to be actually, you get emissions which come from several sources, from traffic here, from factories, from ships, from natural sources like, you know, volcanoes, wildfires, and from agriculture. And there are different types of air pollution. So there are the primary pollutants, which are the ones directly emitted by all these sources. And then the secondary pollutants, which are the ones created in the atmosphere because basically several gases, they kind of like react together and they create these sources. So if you think about it, if you try to see the effect of particulate matter, for instance, on health, it's really important to try and understand what is the source of this PM, because the same level of PM could actually come from different sources. And the source apportionment is really this is the aim of, you know, what the source apportionment is trying to do, is basically trying to disentangle particulate matter into sources where the data come from monitoring station and the data come from chemical, they are related to chemical component or particle concentration by size. And the second one is what we have done in our project. And why it is important to do so? Because really we want to assess if there are different toxicity for the different sources. And once we have assessed if there is different toxicity, we can actually try and develop strategies for reducing these sources and, you know, kind of like and create some sort of, put in place some policies to help people basically and improve population health. So there are challenges, and if you look at this, basically this is the particle sizes here on both axes. It's just a correlation really. The particle sizes come from is really a large spectrum. So it comes from really, really tiny, about 10, 15 nanometers, to quite large, like 400, 500 nanometers. So you get loads of data, and they're very correlated. So I am sure in the mind of all of you, you are immediately thinking about dimension reduction, which is exactly the way we are kind of like going with that. And this is where actually we started with the project. So the project was very specific. We had a very specific aim, which was to try and find a statistical modeling framework for apportioning particle number size distribution. And then we had a real clear application, which was some data from Gatwick Airport. I'm going to say something about the data in a minute. So we had a monitoring station around Gatwick Airport, and we just wanted to see if we could find this framework and apply to this data and see what sources we could get. So obviously, I'm just really a representative of the group. You know, the group has done all the work. So we've done all the work together. It's been really a nice experience, I have to say, even though I sympathize with some of the challenges that Matt was talking about. So the people involved are here in alphabetical order. And then we also had some external collaborators, particularly related to the data. Yeah, so basically the data came from a previous project, and these two people here are two environmental scientists who were involved in the previous project. So the group spanned across 4 universities in England, Canada, and Argentina. So the data we have for this project was coming from, as I said, Gatwick Airport. If you are not very familiar with the UK geography, it's just 40 kilometers more or less south of London, so really quite towards the south part of the country. And here is where the monitoring station is. So here is the airport, and the monitoring station is really just north, very close to the runway. And another thing to say is that the area around here is quite rural. I mean, there aren't really major cities apart from London, which is quite, you know, the 40 kilometers to the north. So really here is a good way of trying and picking. Basically, the idea was to try and see if we could pick emissions from the airport and then see what else was there. The study period is a bit less than a year in 2019. And we had bins of these particle sizes ranging, as I said, from very, very small to quite large. So this is the range. We had it aggregated in 28 bins, And then it's a time series, so it's only one monitoring station, but we had different time steps for each day. So they're kind of like put here. So it's early morning, rush hour, like morning, then early afternoon, and so on. We also had hourly wind speed and wind direction from the NOAA database. And we use the word met package. And I'm just saying this here because we're going to use it. I'm going to tell you in a minute why we use it, basically. So going back to the idea about dimension reduction, basically looking at the literature, this is the approach that has been considered mainly in the environmental science field. Basically, it's a factor analysis. It's a factor analysis where you have your outcome. So it's either the particle size or the chemical composition. So P is the size or the components, and T is the time. And then you disentangle in source profiles, which map basically the chemical components or size to the sources, and then the contribution of each source to the total particle concentration. He has an additional constraint, so it's called positive matrix factorization, this specific one. He has an additional constraint that basically you need the loading to be positive. But that's quite big. You can think about it as a really just as a factor analysis. And what you're kind of like getting out of this type of approach is something similar to what we have here on the right. So you get, in this case, is PM 2.5, and basically you disentangle it, you separate it into the different percentage. So basically the 16% of the concentration comes from secondary aerosol, 66% come from vehicular traffic, but you can even disentangle the emissions, the tailpipe emissions, and the ones which are not exhaust, which I find really interesting. This actually is a big component. So it's the tire, for instance, kind of like on the road and scratching the road and getting particles out of that. And then you have industry and so on. So once you have something like this, you can obviously just target there. You just go in there and say, listen, we have to reduce this 16% or, this 6% or whatever. Actually, this is another important one, which is biomass burning, and it's quite easy to reduce in specific countries. I mean, I'm not talking about low middle income countries, but if you think about the UK or the US, this should be quite easy to reduce. And then you can try and link it with health if you have health data. Okay. What are the limitations of this type of analysis? Any factor analysis is the number of sources you have to define a priori. You don't really include uncertainty on the allocation, and there isn't really dependence in space or time. Obviously, in this case, we only had a time series, but it would work exactly the same if we had space. So this is not really considered. So what we decided to do as this first, first step of the working group was to focus on a more kind of like data-driven approach, which gives a high degree of flexibility. So the number of sources we get it from the data, we can propagate the uncertainty fully, and we can include the temporal, in this case, dependency per se, or even in terms of covariate dependence. So we went to the Bayesian approach, and we went to the Bayesian non-parametric approach, and in particular to the Dirichlet process. So just a very brief recap in case you are not familiar, you forgot about it. So if you have a set of observation x1, xn, which are dependent on a set of latent parameters, θ1 and θn, you can model this theta as a Dirichlet process, which depends on these two kind of parameters. You have a base distribution, actually, so it depends on a distribution and a parameter. This F0 is a base distribution. It basically says the center of this non-parametric distribution, and the precision, just as the precision would say, express the strength of belief. So how confident you are on that center distribution basically gives you an idea of the variability, as the precision would always do. Now, there are several ways of using Dirichlet process and define Dirichlet processes. What we used here is something which has been used before in a very similar context of multi-pollutant studies. So we use the stick breaking prior. So basically our F is an infinite mixture of this delta with this weights. And basically for these weights, you can think of this stick of kind of like length 1, and then you start splitting it. And then basically this V are where you split the stick, and the V have a beta distribution, okay? Now in this formulation, you can see here, K is the sources. It doesn't really depend on anything else, the P, and it's fine. However, we said we kind of like, we want to see if there is a dependence in, it's quite likely actually in this context that there is a dependence in time, okay? And lucky for us, there was something already available. So an extension of this Dirichlet, stick breaking process, this kernel stick breaking process, which was used more in the spatial setting by Dunstan Park and Reich and Fuentes. And basically what happens is that this P now depends on this Q. And Q is a covariate dependent probability weight. And basically now what happens to the V is that the V depends on Q, and this omega KQ is actually kernel function. So it's sort of like act as a smoother, okay? Excuse me. Now, obviously, this could be dependent on covariates. It could also be dependent simply on time, okay? That would be fine as well. But what we wanted to do was to make it dependent on covariates. And I'm gonna skip this because I'm kind of like already talking through it. In particular, we wanted to make it dependent on meteorology. Meteorology is really important in air pollution studies, basically, because you have that the way the particle dispersed or diluted can be driven by meteorology. In particular, the wind is a very important covariate, so we decided to start with that. And in particular, we want to consider wind speed and wind direction. It's kind of like the two information we can get from wind. And we included this into the model with some sort of transformation, some Cartesian representation, which is explained here. Is nothing very complicated. It has been used many, many times before. It's just use sin and cosine and kind of like transform the original values into this Cartesian coordinate. So we had all this information in the model, and this is what we get out of the model. So we run the model and we get some source profiles. Great. So basically now you have to remember, just forget all these things which are written here. What we get out of the model is just a 1, 2, 3, 4, 5, up to 9, and some profiles. And that's where the real trouble starts, because you have to interpret what you get out. And this is where the project really needs to be multidisciplinary. And I think it was great to be able to have someone from the environmental science field helping us. Otherwise, we would have been quite lost, I have to say. So the external collaborators, they were kind of like helping us interpreting this. Because just looking at this, yeah, we can say that we got 9 sources. It looks as, so this is the distribution of the particle sizes for each source. They seem to kind of like cover more or less the domain of the particle sizes. They're quite separated, I would say. What are they? Not sure yet. The other thing I can say is that comparing with the PMF, so with the positive matrix factorization, we found 3 additional sources. So the one with the dashed line are the ones we found on top of the others that they also found. So it was reassuring to see that we could find the same sources. We also found 3 more. Okay, now how do you interpret this? Well, as I said, you need help from some sort of like someone in the field. And you also can use information on the profiles of the sources. So we had, remember, we had different time of the day. So we had kind of like data split into different time of the day. So you looking at sort of like how the different sources were doing in terms of profiles across within the day and across days really helps, because you can identify peak times, you can identify seasonal effects, and so on. The other thing you can also include in your interpretation is the covariate that you're including in the model. So for instance, in our case, the wind. So just to give you a very quick example of these 9 sources, I'm just going to focus on 3. we found one which was pretty big, so 25–26% of the total concentration. The wind was coming from the south, so the sort of like lighter means stronger, okay? And we could see daytime peak, so it was going really down during night, and there was some seasonal variation. So actually that was quite in line with an airport specific source, because actually the airport is south of our monitoring station, and then it kind of like makes sense, you know, you see much more in the day, and then it goes down in the night. This one here is like about 8% with strong wind coming from the north and commuting our peak. So this must be something kind of like urban, because as I said, there aren't really other big cities around the area there, but London is really north. So it kind of like that could also be you know, interpreted in that way. And this here, this biomass burning is one of the sources that was not identified with the PMF, and we could identify. We thought it was biomass burning because you see a strong seasonal variation, is lower in the night, is also correlated with other pollutants that we had available. So I didn't say, but we had information about nitrogen dioxide, nitrogen oxide, carbon oxide, and so on. So really looking at the correlation, we could see that this was fitting the biomass burning. Okay, so I just want to conclude, and I would like just to say that data-driven approaches are very flexible. Obviously, we all know and love data-driven approaches. However, in this particular application, and I think it's the only application, but in this particular case, we really need something which is interpretable. So kind of like using different methods, we may try to use different methods to increase robustness of the results. And obviously, as I said, it's very important to engage with the sort of like experts, making the project very much multidisciplinary. Now, for the future, we would like to compare, possibly in a simulation study, comparing the kernel stick breaking prior with something which is still a kernel stick breaking prior, but does not depend on covariates, but maybe just depends on a time evolution, and see what happens. We are also now exploring alternative methods, in particular from functional data analysis, which are going to be much faster, and it's going to be really great when we can compare and see what we get. And then the last thing is we, in the future, I mean, a very important part, and I don't know if it's going to be in the TIES working group, but in general, when you get this type of outcomes, then the next step is try and link it with health, which opens up another Pandora box, because obviously you have increased computational burden. You need to decide how to propagate the uncertainty. So it's kind of like, is it a joint model that you want to do, or is it a two-stage? You need to decide on the dose response function. You have the usual problem with confounders and so on. So I'm just going to finish here. These are some of the reference. And I'm just really to conclude, I just want to point to the paper that we submitted and had accepted in Envirometrics, special issue. And here is the QR code in case you want to have a look. And it was really a joint, you know, group effort. And yeah, really, I had fun. I hope the others had fun too. Thank you.
Thank you so much, Marta. Absolutely interesting talk.